Serenone from Sao Paulo. We'll talk about initial condition in isobar collisions.
Okay, thank you very much. Thank you for the audience for being here. So the title that was assigned for me was for initial conditions, but just for context, I will not be restricting myself just for the initial conditions. If we the overall these lines here were not supposed to be here. It's a fact for the PDF, but anyway. The general model for the Arriaga collision, we work with usually in this hyperbolic coordinate, so that's the reason for the parabolas, and we have this are high contract nuclei, these conflicts that they travel to each other, and the positive for the energy that we are dealing essentially instantaneously. And well, the point is we divide it in each one of these models of these stages into different models that are mapped to initial we have different models for each one of these stages. So for energy deposition, which is what most people are talking, we usually use some Monte Carlo based global based models. And next to it, we have the most likely this energy deposit is not in equilibrium. It's most likely out of equilibrium. So we usually include a pre-equilibrium phase. Then each one has it also has its different implementations, different models, competing models for this out of equilibrium phase. The system expands, it thermalizes, or it hits local thermal equilibrium, sorry. And this is what usually people use with hydro. All these phases, it's the confined phase. At the energy we are dealing with the transitions through a crossover between the confined phase, and there's the hard phase that people usually employs afterburner to simulate. So my point is, in each one of these stages, we have a different software, different piece of model that we are using, and each one of these models they come at usually different speeds. So usually the initial condition is very fast. The models the out of equilibrium phase, it's also pretty fast, but then we hit hydro, and even though there's a lot of codes that are very performs very well, it's usually our bottleneck on the simulation. So what people try to do is, let's see if we can look at the initial state of the hydrodynamics. So after the pre-equilibrium phase, and see if we can just map to the final state. And there was several talks already here of people that showed results. There was yesterday's talks of Jacques, and there's this is just two examples. There are other publications and the literature. So what I'm trying to do, I will look at the initial condition. I will be using Trento, and then we have one pre-equilibrium stage. That's the free stream, wide free stream, because the idea is that this free stream, this pre-equilibrium phase will erase some of the information we had of the initial condition, and the longer it comes, we expect the worse is this loss of information. So for the typical scales that we believe there's this pre-equilibrium phase, how bad we are, how much information do we lose? That's the idea that I'm trying to, the main idea that I'm trying to answer here. What we do for the nuclear, I'm from the Arriaga community, so I did what I just the most elementary thing. I don't believe that's the most advanced thing that one could do. That is just what everyone do. Just we have are defined with saxons. We have the quadrupole, octupole deformations, the textual parameters, and we example nuclear positions according to this distribution. And I think the one thing that I did that it's a bit out of the standard, not very much, but anyway, it's just I take care to not have overlapping nucleons. So there is I have this minimum parameter that when I try to put a new nucleon, if it's nearby, it's the minimum distance to all other nucleons that it's already there, it's violated. I just throw away it and try again to I can distribute everyone inside the nucleus. And we do this for 6 different cases. So we start with what would be a triaxial tanium, and then I just was change one parameter each time. So case 2, I remove the triaxial parameter. Case 3, I decrease I introduce the octupole. Case 4, decrease the quadrupole parameter. For case 5, I increase the diffusiveness, and case 6, I reduce the radius, and in this way we leave it what people call tanium and go to the zirconium case. So that's the our idea. And for the simulation itself, for the community, what I'm doing is essentially I use the Jetscape framework just to show that the free stream phase. And since it's a framework, it's very easy for me to open it and ask it, implement the calculations of the parameters that we want. So I ask it to give me the initial eccentricities, the ratios of total energy by the divided by the entropy, and so on and so on. And the only thing that I do is just have this nuclear configuration generator that generates my nuclear configuration. That's what I supply to the Jetscape framework. The parameters that I'm using, it's the one from their Bayesian analysis. And what I do, I choose 3 different free stream times. So it's 0.4 farm per C, 1.0 farm per C, and this variable free stream time, which is people might ask, could it happen if I have, let's say, a very small mean initial energy overlap with the 1.0 case? And we looked at it, and the fact that since the power is very small, so the dependence is very weak, and we don't have a large variation. So this variable time, you can understand for practical purposes, that's approximately around 1.4 farm per C, the typical scale. Okay. So anyway, we now start look at the observable. So here, what I do, I look at 4 elementary observables. It's eccentricities of 2, 3, 4, and the inverse of the mean square root of the radius. And I compute this at free stream at the initial condition and make the ratios of free stream over the initial condition. And what we see is so we see 3 grouping of lines. Each one of these are for different or 3 different free stream time. The general behavior is what we expect. We see reductions of the eccentricities, and the radius will increase. So the inverse of the radius also decreases, and all of them kill one together with another. So that's the general look, and it's quite of boring. And because the problem is we should be looking at the details. So we need to. So now I zoom into the details and see what are the differences between the systems. And to do this, I take the case 6, which is the zirconium-like nucleus, and I use as the denominator, and now I compute the ratio of taking initial condition, a case of the zirconium in the denominator, and all other denominators, and then the same for streaming and so on. And since I return, I'm sorry, if we return to this plot, so just briefly, I forgot to mention, we see that the changes with this 0.4 case, it's very small. So for here on, I will not deal with this 0.4 case and just look at 1.0 and the variable free stream time. So I think the main point here, if we look at just this plot and look for mid-central to central collisions, where we believe that hydrodynamics is more robust, we don't see any difference between the initial condition, or very little difference between the initial condition and the after pre-streams. So that even though the free streaming times were raising our information of eccentricity, reducing the eccentricity, we still keep the ratios equals to one another, and we do lose this information. The other things are some well-known effects that we see at central collisions, that when we go from case 2 to case 3, that's when we introduce the octopole deformation. So for those lines from the cyan to the red color, we see that it affects epsilon 2, and then from the red to the magenta, which is removing the quadrupole deformation, it decreases epsilon 2, which is pretty much what we would expect. I tried to looking at things that would be related to two particle correlations and for particle correlations, and the decision of mid-central to central, it does not make a lot of difference. Maybe for epsilon 2, 4, we start maybe to see some effect of the pre-stream, but it's really large, really hard to make a conclusion based on that. We looked at also to epsilon 3, we don't see effect on this case as well, and just the expect things. So difference between due to the octopole deformation. For the quadrupole deformation, that is the magenta with the head, we don't see any difference in diffuse. It's now we see it plays also a larger role here. And just because I had this data on my drive, I did also epsilon 4, epsilon 5, epsilon 6. They all are very similar, and we see mostly the effect of the diffusiveness. We can see a bit of the effect of the different radius. That's just because the head, the yellow line, it's slightly above one, so there is a small effect with two different nucleus size as well. And then I believe it was here in a smaller scale, but it was here on epsilon 32. Okay, for the mean radius, this is interesting because there are suggestions that this could be related to the mean PT. So if we look for case 1, 2, 3, 4, so that's changing the quadrupole, octopole deformations and the triaxial parameter. They have a small effect, but it's not very noticeable. And the two things that we see also changing, it's due to to the diffusiveness and for the mean radius. They are the two things that seem to matter most. But in any one of these cases that I showed so far, we don't see an effect due to free stream. So that main question that I was making the answer so far is there we don't see an effect from these things. The other thing that we're looking is the momentum isotropy. So the idea is when we do the input of our initial condition, we just put an energy momentum tensor that is symmetrical, and that's because the system is static. We put it essentially at the transverse direction. After free stream, the system will not be more at rest. It will be carrying momentum, and it might be having more momentum in one direction than another. So what I do is compute essentially the total difference between moment in the x direction and the y direction, normalized by just the sum of the moments to get sense of this momentum direction. And this will not make sense for me to compute at the initial condition phase, because this is just because of how we initialize this trivial is 0. So that's one thing that we can only look the effect at the pre-streaming stage. So that's something that should be present, should be incorporated in how we do predictions of the system. And we see that it's very in some ways it's very similar to what we see on Webson 2. So there is a difference of both the octopole and the quadrupole deformations as well, but now we have an effect also due to the diffusiveness. And if we look at the diffusiveness case, for example, we see that it's now a bit more sensitive also to the time of the free stream, which makes sense as the system, we allow this to evolve for more time, it will gain more momentum at the cost of losing the anisotropic information, spatial anisotropic information. Okay, so far the only thing that we see that we should be here take account of pre-equilibrium phase is for this momentum anisotropy, and the other thing is that so far we have not seen any observable that's sensitive to the terrestriality parameter. The solution to how to see the effects of this is all known, and the idea is, I think it was already explained here, so I just try to very briefly say it's just that if we have this triaxial nuclei, it has at least let's say 0 impact parameter collision, at least 3 possible configurations. So let's say a chip-chip, a body-body, and another kind of body-body collision. Each one of them will have a different overall size that's carrying the same energy and the different eccentricities. So each one of them will result in a different INT. So I'm using here this plot in this work. They use the energy divided by the entropy. So this is about that constant entropy as estimator of the INT. And what happens is, since they have different INT and different eccentricity, we could correlate them to see if they have we can differentiate between this case. And we did this on our work. The main limitation here is that this requires it's like a three-particle correlator, so it requires a lot more of statistics to compute. But we can see, if you look at the blue line versus the cyan one at the central collisions, we see a difference. We see a effect here. So it's just at these two points here. So it is also sensitive to beta 2. There is a large jump from the red one to the magenta one. And for completeness, I did also for the HO3. HO3, the main difference will be at beta 3 as expected. There is an effect for gamma, but it's not very large as well. I don't present here the free streaming after free streaming case here, just because we are still running simulations, because it requires a lot of statistics, and free streaming starts to be a bit more expensive to run than the initial condition. Okay, so the last thing that we did, we expect that if you compute for the ratio of a given observable for obtaining zirconium, we could parameterize these ratios for a given observable in this way that we're presenting. And this usually the formula is presented only to the C4. So for the 3XL parameter, I'm just guessing a constant times the delta gamma. This is highly work in progress, so I'm open to feedback. And I show some things that are not working quite well. But the idea is what we do here for each one of observables. So for the eccentricities, for the holes, and so on, we compute these ratios. And if you isolate, let's say, the case 3 and case 4, the only thing, if you look at your table, the only thing that changes is beta 2. So all others deltas will be 0, and we can easily isolate C1. And we can do this for all the our cases and obtain these coefficients. And the idea now is we can now use these coefficients and take one case that we did not look yet, that to compute this observed. That is the process that we did. So except to obtain the C3, I never use the ratios where the case 6 is on the denominator. So that would be a way to test if these coefficients are not depending on exactly what kind of system, what kind of parameters I'm making the ratios. And the results that I got for epsilon 2, epsilon 3, and the O2, that are things that most likely, at least for mid-central collisions, should be linearly mapped to the final state. We see that it works well for cases 2, 3, and 4. Cases 1. So here, just to make clear, the bands are the prediction that I made from applying this the formula of the ratios, and the points are the actual ratios that I computed. So just to show where it's not working, if you look at, say, at the epsilon 3, the blue case, it does not match the cyan one. These two bands should be on top of each other, yet we predict that they go differently. And for the yellow one, it's systematically a bit below of the data. So these are the two things that are not working very well. We're still trying to figure out if it's really it's the last to figure out if it's here something of more on our computations, or if it's really a feature and we should go back to this formula and make different assumptions here. Okay, so just to summarize, we show the effects, or in some cases the lack of effects of a pre-equilibrium phase, the free stream several estimators of final state observed. So that's mostly the epsilons, and the hosts. The thing that I would say is similar should also be applicable also to other models, because the free stream is like a worst case scenario, because it assumes that the particles will not interact. So other models such as Glasbar compost, they have some sort of interaction, some kind of dynamics behind that should preserve better the results. So I would say that this sensitiveness in this the ratios after the pre-equilibrium phase should also not change. And the other thing is that if we believe that these estimators are good predictors, these CNs for a given isobar system, so in our case, butane zirconium, if we could isolate their values, we could then try to apply this to isolate the deltas from the wood Saxon. But that's, well, it's a work in progress yet. Thank you, everyone.
Very nice talk. Are there questions? Yeah.
On slide 28, we have the P5 delta gamma. I think like from observables, we always observe that the dependency is in cosine of 3 gamma. So wouldn't it be like P5 delta cosine of 3 gamma rather than just delta gamma?
Yeah. On this work, I try to put
all I'm saying is it might not be linear in delta gamma.
in the okay, you say put cosine of delta gamma.
Delta of cosine
Cosine of 3 delta gamma. Okay, I can try this.
Yeah, I want.
Yeah.
On slide 23, you said that this free streaming, like you do this in zirconium and it's sensitive to beta 300. Do you think this statement will also hold for like large systems?
For large systems,
Do you like larger systems and probably?
well, in a larger system maybe, so that I haven't thought about it, but my guess right now would be that maybe of the case of A would be less significant, because I believe the nucleon, the diffusiveness with respect to the bulk of the nucleon would not be as large. But that's I would have to think a bit about it a bit more.
There's a question, Fushan. Go ahead.
Yes, hi. I have a very technical question. At the beginning, you said when you prepare the nucleus, you require a minimum distance between the nucleons
Yes.
to take into account the hard core potential. Now you say that if you have a nucleon that is within the minimum distance, then you throw away this nucleon and randomly sample another one.
Yes.
Do you mean that you throw away the entire nucleus or just throw away that particular nucleon?
No, just that nucleon that would go on that position. I just say I will not use this position. I will sample another position.
Yeah, and I know that there is a problem with that. So when we do that, we throw away the entire nucleus. We start off from beginning.
Yeah,
Because-
yeah. You are not the first one to say this. The point here is that I was not trying to exactly reproduce everything. I was just focused on the effects of the free stream. But I completely agree.
Okay.
This procedure needs to be made with a bit more of care.
Yeah, it was learned in a very hard way experimentally 20, 30 years ago. Yeah.
Okay,
Okay. Are there other questions?
Thank you.
thank you for the suggestion.
Are there other questions? Right, if not, let's thank William once again. We can go to coffee break a little bit.